All right. Any questions? We ready? Okay, we're going to start off with it's not really Cal 2 yet. I mean, it kind of is, but it's not gonna look that different. And for some of you, you may be familiar with this already. All these notes that I'm going through here are online. All right. So if you go into Canvas and go into Files, you can print these out if you want, or if you have a tablet or something, you're free to have them, in front of you. So I don't expect that when I go through a definition or something, don't be sitting there writing it all down. I mean, because you have access to this, all right? This is more about you just understanding, asking questions, processing it. You have the video you can always go back and watch, right? So I'll move kind of quick through some of these topics. All right, so 3.5, kind of a big picture of what we're doing right now. And I think next class I'll give you like the bigger picture of Cal 2. All right, but for now, let's just look at just what these next two sections we're going to cover today are. In pre-Cal and in Cal 1, you deal with the basic 6 trigonometric functions, right? Sine, cosine, tangent, and then their reciprocals. And you probably in pre-Cal also talked about the inverse trig functions. So in Cal 1, you learn what the derivatives of the 6 trig functions are, right? Derivative of sine of x is cosine of x, right? You learn all that in Cal 1. Here what we're going to do is we're just going to make sure that everyone knows what the derivatives of the inverse trig functions are, okay? Because those functions have derivatives also. So the first part of this is just reminding you what a one-to-one function is, how we can use a horizontal line test to test whether or not a function has an inverse. So this is all like college algebra stuff. We use a vertical line test to test whether or not we're looking at a function. And, here's our standard sine function, right? Is it a function? Yes, passes the vertical line test. Does it have an inverse? Well, does it pass the horizontal line test? It doesn't when you look at it like that, right? It fails. So it doesn't look like it has an inverse. So what we do is we restrict the domain. And when we restrict the domain, then we have an inverse function. So we have to keep that in mind, that whenever we're dealing with the arc sine or inverse sine function, we are on a restricted domain. This is on a restricted domain, right? And that goes for cosine and tangent. All of their inverse trig functions have restrictions. So here's the restriction. So what we do is we just look at the sine function right there. Right? If we just started out at negative pi over 2, ended at pi over 2, just looking in here, it's both a function with an inverse, and then we can define its inverse, right? Okay, so we define it. We use this notation, right? We should be familiar with that notation. And we all agree that inverse exists so long as we restrict sine on that closed interval. What is the restriction for cosine? It's not the same.
Cosine, it's 0 to pi.
0 to pi. Right? And then what about for tangent? How do you have to restrict tangent?
It's the same as sine, so from from negative pi.
Yeah, it's the same as sine except that we don't include the endpoints. So this is review stuff. It's not super critical, just kind of getting your brains going again. All right, so let's see. We have some notation. This is a definition. If we take a function, this goes for any function. If we take a function that has an inverse, and it has an inverse, if we graph them, what's the special property about those graphs?
Domain and range switch.
The domain and range switch, but in terms of the graph, what do they look like graphically compared to one another? They're a reflection, okay, but not over x-axis or y-axis. They're a reflection over the identity. Come on. They put these new boards up here, and I can't, they don't work. Okay, so there's the inverse function. So the red one is sine, and then the blue one is the arc sine. And you can see that if you look at the identity function, which is the diagonal function, y equals x, if you look there, they're reflections of one another. And all inverse functions have that property. All right? Again, this is not really what we're most interested in, just kind of getting our brains going. But let's practice doing a couple of these. So when you are asked to find arcsine of 1, another way of looking at that problem is saying sine of what angle, right, is equal to 1. So when you look at the sine function, you plug an angle in and it spits out a number, right? When you look at an arcsine function, you're plugging in a number and it's supposed to spit out the angle, so it's going backwards. So this is an equivalence question that this is asking, right? So what sine of what angle is 1? So this is all going to depend on you. I encourage and I hope all of you are comfortable with working with your trig functions off of the unit circle. So when you look at the unit circle has a radius of 1. And when we're talking about sine of an angle, we're talking about which coordinate on the y coordinate. If we're talking about cosine, we're talking about the x coordinate. So this question is asking, where on your unit circle is your y coordinate 1? Right? And that's going to happen right there, right? And what is the angle that gets you there? Pi over 2. So the answer here, this is equal to pi over 2. All right, now, could someone have said, this was pi over 2, right? Right there? Could someone have said that the answer is negative 3 pi over 2? I mean, because isn't that the same place? I mean, if you can go this way, counterclockwise, or you could go clockwise. Can this be an answer? It cannot. And the reason, now, we have to be careful with this. Do you agree with this statement? Do you agree with this? Is this true? Yes. That is true. That is true, right? However, when we're saying arcsine of 1, we are restricting ourselves to only looking between, we said, negative pi over 2 and pi over 2, which means you're only allowed to look here and here. So in other words, the left side of this circle, you're not allowed, oh, that's a nice one. You're not allowed to travel into the left part of this circle, right? So you cannot go negative 3 pi over 2. You understand the difference? This by itself is true, but you cannot say that this is equal to negative 3 pi over 2. Okay, look at the next one. Arcsine of root 3 over 2. Can you all see that okay? I have the lights off up here. That's all right. So when we say the next one, we still have to restrict ourselves, right, because we're dealing with arcsine, and we're saying, where is this equal to root 3 over 2? And so at what angle, so where on your unit circle is your y coordinate root 3 over 2? So pi over 3, that's like right up here, but it's also root 3 over 2 right there, isn't it, at those two locations? But we can't have two answers, right? So we know we're not allowed to travel over here. So the answer has to be this angle, which is pi over 3. Okay, so this would be pi over 3. All right, this is all, does this look like remind you of pre-cal? Yeah, okay. We might need to evaluate these later, so I just want to make sure we have that clear. Now, I've already said that all the other trig functions have inverses, but we have to restrict their domains. I talk about here cosine, the restriction is between 0 and pi. Where do I just said right here. And then arctangent has restrictions, and then you can look in your book or back to your pre-cal stuff if you want to go and have those. You don't need to have those well, sine and cosine and tangent, those three you should know how the restrictions are for their inverses. The others, not as important. All right, we have a very important property called the cancellation property. This property is used incorrectly quite a bit. It just says that when you use composition, sine of arcsine of x, that it's just going to spit out the x. So in other words, the two functions kill each other off. But this only works when x is between negative 1 and 1. And you can go the other way with the composition, do arcsine of sine of x, and it'll spit out x so long as x is between here. Let me show you an example of this one being used incorrectly. Let's go. Let's see if that's going to do it. Okay, so what would be the incorrect way to look at this? What would be incorrect? Equal to 2 pi over 3? Is that right? This is incorrect. Okay, so that's someone looking at that property and thinking, oh, it's just they're going to kill each other off and just spit out x. And that's not correct because the answer has to be between negative pi over 2 and pi over 2. And this answer is not. So how would I do this problem? If I were doing this, all I would do is I would just look at this inside part and I would just go to my unit circle. I go to 2 pi over 3, which is over here, right? I'd say sine of that angle is the y coordinate. So what is the y coordinate there? It's negative 1/2 root 3 over 2. Okay? So this part, this is arc sine of root 3 over 2, isn't it? And now, isn't that the problem we just did? And what was our answer? Pi over 3. Okay? So that, just be careful with that cancellation property. With certain ways you put them together, you can get yourself into trouble. All right? All right, now, why are we here? The derivatives. That's really what we're interested in. Now, just a show of hands, does anybody recall in Cal 1 going through the derivatives of the inverse trig functions? Did anyone do that? You did? Yeah? Okay. So this is where there might be a little overlap. Some teachers do it, some don't. I don't remember doing it, James. No? We did? We did? Okay. All right, so derivatives of the inverse trig functions. In order to prove to you, so what I'm going to do is I'm going to show you right now how we can determine what the derivative of this arc sine function is. I mean, it has a derivative, right? Hopefully. It's a function. Hopefully it's differentiable. But to do it, to actually show you what the derivative is, I'm going to be using a couple of techniques that are going to be critical in this class as we move forward. So these are skills that you will need later. So this is a great time right now to actually use them for something else. So I guess what I'm saying is what we do here, there's little bits and pieces of what we do here that you're going to see again. All right, so how do we find the derivative of that? So I'm going to write this down. Okay, we want the derivative of this, right? We want y prime of x, or y prime, sorry. Yes? So I don't know anything about what that derivative is, right? I mean, if I knew the derivative, I'd just put it down. I could look in my formula sheet, it's there, right? But if we didn't have the formula sheet, how would we come up with it? So what I'm going to do first is I'm going to try and use this cancellation property. So I'm basically composing sine on both sides of the equation. All right? Now, on the right side, this should just be what? X, so long as the domain restrictions are satisfied, which we're just going to kind of like wave our hands at it and be like, okay, we're going to say that this is true so long as everything is met. All right? And then the right side is sine y. I won't put it in parentheses this time. All right, now at this point, we're going to differentiate both sides of the equation implicitly with respect to x. So I'm going to take the derivative with respect to x on both sides. So if I take derivative with respect to x here, I go derivative with respect to x of sine y equals the derivative with respect to x of x. Now, I'm not sure how this notation looks to you because there are little slight differences in notation in calculus 1. Does this all look somewhat familiar to you? Okay. Now, let's do the right side first because that's the easier part. What is the derivative of x with respect to x? That's just 1. So this is just 1. And the left-hand side, we have to take derivative with respect to x of sine of y. So derivative, we have to do like a chain rule here, right? Derivative of sine of something would be cosine of that y. And then times, this is the most critical part right here. Chain rule says you now need derivative of what's inside. So dy dx, or you could write y prime. Again, that depends on what you saw in the past. I'm going to put dy dx. Okay, so that's your chain rule right there on the left-hand side. And that is what we're trying to find, right? dy dx, that's the same thing? Yes. Okay, so we just need to isolate this now, get it by itself. So I'm going to just divide both sides by cosine y. And so my answer here is dy dx equals 1 over cosine y, but we know 1 over cosine y is really secant y, right? So our answer is secant y. Yeah? Okay, now, if you go look in your formula sheets, you're not going to see that. You're not going to see that the derivative of arc sine of x is equal to secant y. And the reason why is because, look at this right here, your answer, you need to have y, don't you? But our original function is a function of x. So we would like our answer to be a function of x also. So right now what we're going to do is try and switch this back to an expression that has x in it instead of y. So to do that, what we'll do is we will use a reference triangle. Are there any questions up to this point? You all okay with this? I'm not going to pull these sticks right yet, okay? Maybe in a little while. Start putting you on the spot. All right, so we are going to do a reference triangle at this point, and I don't really have a lot of space here. Let me see if... There, I'll do it right there. So, reference triangle. Now, what we mean by reference triangles, we're going to draw a right triangle. What we're going to do is we're going to construct this right triangle using this line right here, the line after we did sine on both sides. So this right here says sine of some angle y is equal to x, right? Now I'm going to come over here and let me put something in this triangle. I'll put y here, x here, and 1 right there. Now look at that triangle I just made. Does that triangle match up with this equation? Sine, by definition, sine is which side over which side? Opposite over hypotenuse, isn't it? So we could look at this sine of y being equal to x as being like x over 1, couldn't we? Right? X is x over 1. And so if I look at this and I ask you, hey, look at this triangle, what's sine of y? Everyone would say, oh, sine of y is x over 1. You'd say it's x, right? So these two match, don't they? Now what's important about that is we're interested in what secant of y is, right? Yes. And secant is the reciprocal of cosine. So if we could just figure out what cosine of y is, we'd be in business. For cosine of this, we need the adjacent side, right? But we have 2 of the 3 sides of a right triangle. So we can solve for this side just using the Pythagorean identity. Now I'm not going to go through this, well, maybe I should. It's the first day. So we'll just call this a for adjacent. We know that a squared plus x squared equals 1. And we can solve this for a, so a squared equals 1 minus x squared. And that means a is equal to the square root of 1 minus x squared. I should do plus or minus here, shouldn't I? Because I took square root. Yeah. But because a is the positive length of that side of that triangle, I'm going to just look at the positive, right? So that's what a is. So this side is really equal to square root of 1 minus x squared. And so now I can come back over here. I can get my answer in terms of x. Secant of y is the reciprocal of cosine. So instead of doing adjacent over hypotenuse, I'm going to do hypotenuse over adjacent. And that's my answer in terms of x, isn't it? And that is the formula you will find in your formula sheet. The derivative of arc sine of x is equal to 1 over the square root of 1 minus x squared. Okay? Any questions? We could do this for all of the trig functions. Like if you wanted to do in the next one, and I think in your homework there's a few of these. Like if y is equal to arc cosine of x, find the derivative, right? Then you would do what on both sides? Cosine on both sides, right? And then you would differentiate implicitly with respect to x, and then you would do a little right triangle, and then you go solve, and you would get the same thing happen, right? Now your answer would be different, but slightly. Okay? All right, so that's it. You do not have to derive these, okay? They are on a formula sheet. On your test, you will use your formula sheet, but it's good to know where they came from, right?
Yeah.
All right, moving on. So, you know, in Cal 1, you do these kind of like, you progress through derivatives, right? You start with the limit, and then after the limit, you define the derivative using the limit, right? So the derivative function is the limit as h goes 0 of f of x plus h minus f of x all over h, that thing. Then you like mess with all that. It's real nasty. The algebra sucks. And then they give you the shortcut rules, right? You get the power rule, you get the product rule, chain rule, right? Quotient rule, chain rule. And so as you move through Cal 1, as you start to introduce more functions like the exponential and log, all those rules are in play. So now we already know product rule, quotient rule, chain rule. So we have this problem right here. Find the derivative of this, all right? So we've gone from arc sine of x to this. And now we are allowed to use this. So that was a one-time thing, me showing you that formula. Now we know this. The derivative of this is equal to 1 over the square root of 1 minus x squared. We're allowed to use that, right? So if I want to take the derivative with respect to x of arc sine of the square root of 1 minus x squared, I'm going to use this formula, but our argument, right, the thing inside here, is not just x, right? It is all of that, right? So we'll have to use the chain rule. So this is, this is going to go back again to Cal 1, see how comfortable are you with this. So my derivative will be, using this formula, 1 over the square root of 1 minus, but not x squared. What squared? The square root of 1 minus x squared, right? That whole thing squared. So I'm actually going to write that down. This is the square root of 1 minus x squared, that whole quantity squared, right there. That's what that is. Now we're not done, right? That was just, when we do the chain rule, we work like from the outside in. So we just took the derivative of arc sine of something, right? Now we got to take derivative of what's in here. So we have to start now at the square root. So I'm doing chain rule, so I have to do multiplication, right? What is the derivative of the square root of something? 1 over 2 roots of that something. So that is the derivative of the square root of this. But I'm still not done. Now I have to go inside the root and take derivative of what's in here, which is times negative 2x. Okay, so if you're having any trouble with any of that chain rule stuff, you need to get yourself back up to speed, all right? Because at this point in this class, I would expect everyone can do that sort of chain rule progression, all right? It's not like the end of the world for you, okay? You don't have to go drop the class, but we need to get you up to speed. And this is one of those moments where you have to say honestly to yourself, like, am I there or not? If I'm not, I go get help, right? And my office hours, which means I'm available to you. This is my only class I teach today. So it goes from 1 to 2:40, right? I'm usually in my office by like 8:30, 9, and I'll be in there all the way till 1 o'clock. So if you can come in, I think officially I have 10 a.m. to 1 p.m. on my syllabus, but I should be in there earlier. So I encourage you, if you need help, come by and get help, all right? Especially if it's stuff that's not in this class, like Cal 1 stuff. All right. Can I proceed? All right, so the other derivatives of the other inverse trig functions can be found in your book and also found on your formula sheet. Go explore those on your own. I will say, this one right here is super important. The derivative of arctangent x. The sooner you memorize this one, the better. That's it right there. We will see this thing so much it's going to kind of make you, like, you're going to get tired of it, all right? All right, we have another example. Let's look at example 4. I'm going to make this a little bit bigger. I want you to work on it. How about you sit there and you work on that one right there. And then I'm gonna pull a stick, and we're gonna see where we are. Can everyone read it? Do your best. If you can't get it, you can't get it. It's all right. Kim, I'm just letting everyone try and work this one out. If you have a question, you can raise your hand. I can come by and help out. You don't need to clean up the answer, okay? Just try and just get the derivative written out. Don't worry too much about the algebraic simplification of it. I'm going to pull a stick. I'm going to pass around an attendance sheet where you find your name and initial underneath today's date. I'll be passing that around the class every day. Well, I'm supposed to, but I probably will forget. So, okay, I think, like, in my opinion, that's plenty of time to do that problem. So if you need more time, then it's just, again, you got to get yourself up to speed. All right, so the lucky student here is Adam. Where's Adam? You're at, okay, so you're no go on this. What is it that you like working on cars, right? Right. So you got good by practice, right? So with all of you, video games, whatever it is, right? Like, you get good by practice. And you may have heard this, and it's not cliche in this class. You are going to fail more times than you're going to succeed in this class. And I don't mean like fail tests and quizzes. I mean, you're going to be doing problems, you're going to be getting them wrong and crumbling up your paper and starting over. And you just have to be that type of person to have that drive, okay, to keep going. All right? You can't. If you quit, then this course will be done. It'll eat you up. All right? So let's move on to the next one. So Scott Christians.
Yep.
Scott.
So I don't.
Can
know
I
if
just
this
look at
is-
it?
I don't know if this is right or not, but I tried doing the chain rule right here.
No, it looks pretty close, except for that, and then this X. This is not bad. So I'm going to go through it, okay? So we could just spend the next 30 minutes with me walking around. Let's talk about. We don't have time, all right? So, but I want everyone to sit here with the pressure that I may call on you, okay? I want that to happen every day. All right. So look, and there's Adam. There's nothing, Adam,
Well, I
right? There's.
kind of an idea, but I just forgot what
But I'm saying you're not like, your feelings aren't hurt. Like you weren't ready, you couldn't do it. Adam doesn't care, okay? Hey, Anna, Adam doesn't care. I don't want anyone to care. The only time that's going to matter that you should care is that test. Okay, that's when it really matters, all right? So if in here we're making mistakes, that's okay, all right? All right, so here we go. The derivative of this. So I first have to take care of the fact that I have the square root of something, right? So anytime I take derivative square root, I do 1 over 2 square roots, and then whatever was in it, which is the whole expression. Okay. Now, if you're not real familiar with this whole derivative of the square root of something is 1 over 2 times square root, talk to me after class. That's the way I teach it. You could rewrite it as like a 1/2 exponent and bring it down and subtract 1 and all that. It all depends on you. But they turn out to be the same expression algebraically. Okay, so I'm done with the square root part, right? Times, now I take derivative of the natural log of something, which is 1 over that something. And so I'm done with the natural log part, right? And then I say times, now I move into the arctangent, take derivative of that, and that is 1 over 1 plus x squared, right there. And these dots between these fractions is enough for me to show that they're separated. Yeah, I mean, that's what I like to call this the raw derivative because we haven't even tried to clean anything up. That's it, okay? One thing, could I have done this? To start the problem, could I have rewritten this and you know what, I'm gonna pull a stick again. So Marissa, you're right here. Could I have rewritten the problem like that, started the problem that way?
You'd have to have parentheses around the actual.
So I could not do this. Does everyone agree this cannot be done? That is correct. You cannot do it this way. You would have to have parentheses here. I guess what I'm getting at is be careful because the fraction, remember like fractions can come down and stuff? You have to be real careful with that because the number right here can only come down if it's on the argument. So like this is equal to this, so long as this n is applied to the x only. Okay? In this case, this 1/2 is applied to the whole expression, including the natural log. So you can't play with it like this. Okay, moving along. So have you all noticed with these sticks, like if I call someone, like they come over here, and then the ones still haven't been called are right there. All right. All right, next one. All right, we're not gonna take time to do this. Let's just go through it together. Find the equation of the tangent line to arc sine of x y squared equals x plus y at the point 0, 0. So I'm gonna go to a graphing utility real quick. For those of you who had me in Cal 1, you know I like to use what? Desmos, okay? I like to use Desmos. I'm sure there's something better out there now, but I like Desmos. So what you can do here is, let's graph this thing. I'm just going to put arc sine of x times y squared equals, I think it was x plus y. Yeah, there we go. Okay, so there it is. There's the graph of that equation. There it is. And we are trying to find the equation of the line that is tangent to this curve at the point 0, 0. All right? We're trying to find the equation of that line. So in order to find the equation of a line, right? How do we do this in Cal 1? In order to find the equation of that, we're going to use the formula y minus y naught equals m times x minus x naught. This is our point slope formula from college algebra, right? And we already know what x naught and y naught are, don't we? Mm-hmm. That's 0, 0. We just need the slope. And what is the slope? Well, that's going to come from the derivative, right? The derivative is going to give you the slope of the tangent line. So we need to find dy dx, right, at the point 0, 0. That's what we need to figure out the slope, right? So where are we going to get dy dx from? Well, we have to take derivative of that, but the problem is this is not solved for y, is it? This is an implicit equation. So back in Cal 1, you did this thing called implicit differentiation. That's what we're going to do here. We're going to do implicit differentiation. The only new element today is that we have arc sine in there. Okay, that's the only thing that would be kind of new. So I'm going to go ahead and start doing the derivative of that. So here we go. I'm going to take the derivative with respect to x on the left side. Must equal the derivative with respect to x of the right side. First day, he's calling on us on first day. Priscilla.
Yes.
Okay, I want the right side. What's the derivative of the right side
With respect to x,
with respect to x?
isn't it 1 plus y prime? 1 plus y, I'm sorry.
Only one thing wrong with the way you said that. You said, isn't it 1 plus y prime? You should say, it is 1 plus y. You got to have that confidence. And then if you're wrong, you're wrong. Who cares, you know? Okay, 1 plus y prime. Everyone agree? So you can do that because there's addition. You can do them separately. Derivative of x with respect to x is 1. Derivative of y with respect to x is dy dx. This time Priscilla said y prime. I'm going to put y prime. That's same as dy dx, right?
Yes.
Okay, now, if I left a parentheses off here, y'all see that? James.
Yep.
This James. Left side. So what rules are we using on the left side? Chain and product. All right, so start me off with the chain. What do we got? Derivative of arc sine of this would be what?
1 over
1 over
square root,
square root
1 minus
1 minus
x squared.
x squared, but this is our x, right? So this whole argument's squared, so I'm just going to square each one of them. Yeah? X squared, y to the 4th.
Right.
Everyone see that? Okay, are we done, James? No, chain rule, right? Times?
Let's see.
Now you have to take derivative of this.